At the end of this video, you should be able to describe the electron configurations for the atoms of any element using orbital notation, electron configuration notation, and, when appropriate, noble gas notation. Chapter 4, Section 3, Representing Electron Configurations. Three methods or notations are used to indicate electron configurations. Two of these notations will be discussed in the next two sections for the first period elements, hydrogen and helium. The third notation applies mostly to elements of the third period and higher. It will be discussed in the section on third period elements. In a ground state hydrogen atom, the single electron is in the lowest energy orbital, the 1s orbital. The electron can be in either one of two spin states. Helium has two electrons, which are paired in that 1s orbital. Orbital notation. In orbital notation, an unoccupied orbital is represented by a line, as is shown on the screen now, with the orbital's name written underneath the line. An orbital containing one electron is represented as is shown on the screen now. An orbital containing two electrons is represented as shown on the screen, representing the electrons paired and with opposite spins. The lines are labeled with the principal quantum number and sublevel letter. For example, the orbital notation for helium is written as is shown on the screen now.
Electron configuration can be indicated by orbital notation. In orbital notation, an unoccupied orbital is represented by a line. The lines are labeled with the principal quantum number and sublevel letter. An orbital containing one electron is represented by a line with one arrow pointing up. An orbital containing two electrons is represented by a line with two opposed arrows, showing the electrons paired and with opposite spin. Look at the superscripts for each orbital in the electron configuration. The superscripts indicate the number of electrons in a given orbital. We add arrows to show these electrons. Once all the electrons have been placed, the orbital notation is complete.
Electron configuration notation. Electron configuration notation eliminates the lines and arrows of orbital notation. Instead, the number of electrons in a sublevel is shown by adding a superscript to the sublevel designation. The hydrogen configuration is represented by 1s1. The superscript indicates that one electron is present in hydrogen's 1s orbital. The helium configuration is represented by 1s2. Here, the superscript indicates that there are two electrons in helium's 1s orbital.
Electron configuration notation eliminates the lines and arrows of orbital notation. The main energy level is indicated by a number. It is followed by a letter indicating the orbital. The number of electrons in a sublevel is shown by adding a superscript to the sublevel designation. The configuration for nitrogen is represented by 1s2, 2s2, 2p3. The superscripts indicate that two electrons are present in nitrogen's 1s orbital, two electrons are present in the 2s orbital, and three electrons are present in the 2p orbital. This configuration indicates that nitrogen has a total of 7 electrons and tells us that nitrogen has an atomic number of 7.
Elements of the second period. In the first period elements, hydrogen and helium, electrons occupy the first main energy level. The ground state configurations in Table 4-3 on page 110 of your text illustrate how the off-bow principle, the Pauli exclusion principle, and Hund's rule are applied to atoms of elements in the second period. Figure 4-19, also on page 110 of your text, shows the first four main energy levels in order of increasing energy for applying the off-bow principle. According to the off-bow principle, after the 1s orbital is filled, the next electron occupies the s sublevel in the second main energy level. Thus, lithium, Li, has a configuration of 1s2, 2s1. The electron occupying the 2s level of a lithium atom is in the atom's highest or outermost occupied level. The highest occupied level is the electron-containing main energy level with the highest principal quantum number. The 2 electrons in the 1s sublevel of lithium are no longer in the outermost energy level. They have become inner shell electrons, which are electrons that are not in the highest occupied energy level. The 4th electron in an atom of beryllium, Be, must complete the pair in the 2s sublevel because the sublevel is of lower energy than the 2p sublevel. With the 2s sublevel filled, the 2p sublevel, which has 3 vacant orbitals of equal energy, can then be occupied. Hund's rule applies here, as is shown in the orbital notations in Table 4-3 on page 110 of your text or on the screen now. One of the 3 p orbitals is occupied by a single electron in an atom of boron, B. 2 of the 3 p orbitals are occupied by unpaired electrons in an atom of carbon, C. And all 3 p orbitals are occupied by unpaired electrons in an atom of nitrogen, N. According to the Aufbau principle, the next electron must pair with another electron in one of the 2p orbitals rather than enter the 3rd main energy level. The Pauli exclusion principle allows the electron to pair with one of the electrons occupying the 2p orbitals as long as the spins of the paired electrons are opposite. Thus, atoms of oxygen, O, have the configuration 1s2, 2s2, 2p4. 2 2p orbitals are filled in fluorine, F, and all 3 are filled in neon, Ne. Atoms such as those of neon, which have the s and p sublevels of their highest occupied energy level filled with 8 electrons, are said to have an octet of electrons. Notice that neon is the last element in the 2nd period. Elements of the 3rd period. After the outer octet is filled in neon, the next electron enters the s sublevel and the n is equal to 3 main energy level. Thus, atoms of sodium, Na, have the configuration of 1s2, 2s2, 2p6, 3s1. Compare the configuration of a sodium atom with that of an atom of neon in Table 4-3 on page 110 of your text, or shown on the screen previously. Notice that the first 10 electrons in a sodium atom have the same configuration as a neon atom, 1s2, 2s2, 2p6. In fact, the first 10 electrons in an atom of each of the 3rd period elements have the same configuration as neon. This similarity allows us to use a shorthand notation for the electron configurations of the 3rd period elements. Noble gas notation. Neon is a member of the group 18 elements. The group 18 elements, helium, neon, argon, krypton, xenon, and radon, are called the noble gases. To simplify sodium's notation, the symbol for neon, enclosed in square brackets, is used to represent the complete neon configuration. Neon is equal to 1s2, 2s2, 2p6. This allows us to write sodium's electron configuration as Ne 3s1, which is called sodium's noble gas notation. Table 4-4 on page 111 of your text, or on the screen now, shows the noble gas notation for the electron configuration for each of the 3rd period elements. The last element in the 3rd period is argon, Ar, which is a noble gas. As in neon, the highest occupied energy level of argon has an octet of electrons, Ne 3s2, 3p6. In fact, each noble gas, other than helium, has an electron octet in its highest energy level. A noble gas configuration is an outer main energy level fully occupied, in most cases, by 8 electrons.
The noble gas notation provides a way to abbreviate electron configuration. In this periodic table, noble gas notation is used to describe the electron configuration of each of the elements. Aluminum has the same basic inner electron configuration as neon. It differs from neon in that it has 2 electrons in its 3s orbital and 1 electron in its 3p orbital. Similarly, oxygen has the same inner electron configuration as helium, to which it adds electrons in the 3s and 3p orbitals. Writing out the entire electron configuration for iodine would take quite a bit of space. Finding the next smaller noble gas and using it as a base makes the notation much simpler. Iodine has the same inner electron configuration as krypton, plus 17 more electrons.
Elements of the fourth period. The electron configurations of atoms in the fourth period elements are shown in Table 4-5 on page 112 of your text or on the screen now. The period begins by filling the 4s orbital, the empty orbital of lowest energy. Thus, the first element in the fourth period is potassium, K, which has the electron configuration of argon 4s1. The next element is calcium, Ca, which has the electron configure of argon 4s2. With the 4s sublevel filled, the 4p and 3d sublevels are the next available vacant orbitals. Figure 4-19 on page 110 of your text, or on the screen previously, shows that the 3d sublevel is lower in energy than the 4p sublevel. Therefore, the 5 3d orbitals are next to be filled. A total of 10 electrons can occupy the 3d orbitals. They are filled successively in the 10 elements from scandium, atomic number of 21, to zinc, atomic number of 30. Scandium, Sc, has the electron configuration argon 3d1 4s2. Titanium, Ti, has the configuration argon 3d2 4s2. And vanadium, V, has the configuration argon 3d3 4s2. Up to this point, 3 electrons with the same spin have been added to 3 separate d orbitals as required by Hund's rule. Surprisingly, chromium, Cr, has the electron configuration argon 3d5 4s1. Not only did the added electron go into the 4th 3d orbital, but an electron also moved from the 4s orbital into the 5th 3d orbital, leaving the 4s orbital with a single electron. Chromium's electron configuration is contrary to what is expected according to the Aufbau principle. However, in reality, the argon 3d5 4s1 configuration is of lower energy than the argon 3d4 4s2 configuration. For chromium, having 6 outer orbitals with unpaired electrons is a more stable arrangement than having 4 unpaired electrons in the 3d orbitals and forcing 2 electrons to pair up in the 4s orbital. On the other hand, for tungsten, W, which is in the same group as chromium, having 4 electrons in the 5d orbitals and 2 electrons paired in the 6s orbitals is the most stable arrangement. Unfortunately, there is no simple explanation for such deviations from ideal order given in figure of 4-19 on page 110 of your text. Manganese, Mn, has the electron configuration of argon 3d5 4s2. The added electron goes to the 4s orbital, completely filling this orbital while leaving the 3d orbital still half filled. Beginning with the next elements, electrons continue to pair in the d orbitals. Thus, iron, Fe, has the configuration argon 3d6 4s2. Cobalt, Co, has the configuration argon 3d7 4s2. And nickel, Ni, has the configuration argon 3d8 4s2. Next is copper, Cu, in which the electron moves from the 4s orbital to pair with the electron in the 5th 3d orbital. The result is an electron configuration of argon 3d10 4s1, which is the lowest energy configuration for copper. In atoms of zinc, Zn, the 4s sublevel is filled to give the electron configuration argon 3d10 4s2. In atoms of the next 6 elements, electrons add one by one to the 3 4p orbitals. According to Hund's rule, 1 electron is added to each of the 3 4p orbitals before electrons are paired in any 4p orbital. Elements of the 5th period. In the elements of the 5th period, Sublevels fill in a similar manner as in elements of the fourth period. However, they start at the 5s orbital instead of the 4s. Successive electrons are added first to the 5s orbital, and then to the 4d orbital, and finally to the 5p orbitals. This can be seen in table 4-6 on page 114 of your text or on the screen now. There are occasional deviations from the predicted configurations here also. The deviations differ from those of fourth period elements, but in each case, the preferred configuration always has the lowest possible energy. At this point, you should be able to describe the electron configurations for the atoms of any element using orbital notation, electron configuration notation, and, when appropriate, noble gas notation.